changed by another process, and this another process is considered to be independent from psi. So these two are independent. Yes, because our waiting times were independent from jumps. Yeah, and so as we have seen in regime number 1, our waiting times were exponentially distributed. But here our waiting times were not exponentially distributed. They had heavy tails, distribution of heavy tails. And hence this inverse process, so beta stable subordinator is a Levy process, it's a nice Markov process. But the inverse to it, generalized inverse process, is no more Markov. And once again, so this time changed Markov process is no more Markov. Yeah. And if you look at this equation, or here in this form, so here we have a generator of a Markov process, but then we integrate with a kind of memory kernel. So there is memory in the system. No Markov property anymore. So this is so to say the summary that we consider this time and space fractional heat equation, and there are two ingredients. One ingredient corresponds to the space. So this is the fractional Laplacian, and it is still the generator of a strongly continuous pairing group and the generator of a Markov process. It's a nice thing. And the bad thing is that we have a memory kernel, so something which corresponds to time. Yeah, because a fractional derivative is actually not a differential operator, but pseudo differential operator, or better to say integral differential operator. So it is not local. It is not local, so it depends not on the behavior of function around some point, but on the whole function. And this gives rise to memory in the system. Okay, so as I said, so here we have this time change. This is a process which is independent from psi, and this process is in the so-called inverse subordinator. So one can show again that this is a process with non-decreasing paths, so it's a nice time change, but still it is a non-Markovian time change. Okay, so actually inverse subordinators, so what I was described here so far, it is like something classical, known already more than 20 years at least, even more. So since that time, these inverse subordinators are actively used to produce stochastic representations of solutions of time fractional evolution equations of the following form. So that is exactly as we have seen here. So this is the generator of a Markov process, and this is a kernel, memory kernel. So we can generalize this to this equation, where n is the generator of a Markov process, and this is the memory kernel, and this memory kernel is a kind of convolution type. Yeah, so kernel here stays as k of t minus s, and then here a function of s ds. It's a kind of convolution. So inverse subordinators pops up if we consider such equations where this memory kernel belongs to a particular class of functions, namely a functions whose Laplace transform has the form 1 over h for some Bernstein function h. As soon as we have a Bernstein function, we have a Levy subordinator, so a Levy process which is a subordinator having this function as Laplace transform. As soon as we have a Levy subordinator, so a Laplace, a Levy process with non-decreasing paths, we may consider generalized inverse to that process, and it will be the so-called, the corresponding inverse subordinator. Yeah? And one can show that this inverse subordinator can be used in the following way. So that is, this xi is a process which corresponds to L, and the inverse subordinator corresponds to the Bernstein function, which pops up in the Laplace transform of K. Yeah, and then this time change process provides the stochastic solution of this equation. So the thing which I want to say that the statement, so that this process is a solution of this equation, can be generalized. So instead of fractional Laplacian, I may consider any generator of a Markov process. Instead of such convolution, I may consider all convolutions which are somehow related to the Bernstein functions, and then Levy subordinators, and then inverse subordinators. That's all what you should know about that. But don't worry, it was just a kind of remark. There is also another approach to model anomalous diffusion. Another approach is based on completely different processes, known as randomly scaled Gaussian processes. Randomly scaled Gaussian processes are processes of this type. So we have some Gaussian process GT multiplied with a random variable which is independent from this Gaussian process and non-negative. So this A is a random scaling. Okay. So the most well-known or first example which has appeared in the literature is the so-called generalized gray Brownian motion. And it looks as follows. It's a fractional Brownian motion randomly scaled by some random variable with a particular distribution. So this square root of A beta, so A beta is a random variable which is independent from our fractional Brownian motion. It is non-negative, and its Laplace transform is given in terms of the special function known as Mittag-Lefler function. So having this particular choice for the random scaling, we consider randomly scaled fractional Brownian motion, and we obtain the process called generalized gray Brownian motion. Of course, it is a family parameterized by alpha and beta, for all possible alphas, which gives us here a Hurst parameter, and for beta, or actually non-negative beta. Beta from 0 to 1, let us consider beta from 0 to 1. I just recall you what is fractional Brownian motion. Fractional Brownian motion is a centered Gaussian process whose covariance function is given by this formula. The power h here is called Hurst parameter, associated with fractional Brownian motion. Then h is equal to 1/2, we just obtain Brownian motion. For other choices of Hurst parameter, the process is not Markov. It does not have independent increments, namely the increments are correlated, and for h strictly bigger than 1/2, the increments of the process are positively correlated. For h smaller than 1/2, the increments of the process are negatively correlated. This means that this process somehow keeps the memory. So fractional Brownian motion is not a Markov process, is not a semi-martingale, and the increments are correlated, hence the process like fractional Brownian motion feel good to model systems where the memory is present. Also, two definitions which probably known for you. So a process is called self-similar if the time change process has the same distribution as the scaled process for all possible A. The process has stationary increments if such increments have the same distribution as such increments for any choice of t bigger than s and any choice of tau. So if you have a process which is self-similar and has stationary increments, and self-similar with first parameter h, this is exactly this power here. So we call that such a process is HSSSI process. Okay, so it turns out that this generalized Bragonian motion is exactly this SSSI process, and the first parameter is exactly the first parameter of the driving volume, fractional volume motion. And actually, SSSI processes are nice for modeling, because if you have stationary increments and self-similar increments, it's nice for
Why
yeah, sorry, it is a typo. It is 8. Yeah, sorry. Yeah, so the thing is that first we follow some authors, which the authors use this white beta, but then after writing our own papers and trying to connect all the objects together, we had to create our own notations, and it is A beta. Yeah, so it is A beta, sorry. Okay, moreover, it was proved in the literature that this GBM, generalized Bragonian motion, provides stochastic solution, stochastic representation for the solution of the following evolution equation. So you see, this equation looks as we wanted to have almost. So here we have u is equal to initial condition plus integral from 0 to t. Then here we have 1/2 Laplacian, it's the generator of a Markov process. And we have a memory kernel, so this constant goes to the memory kernel. So it's a function of t and f. But it is not of convolution type, at least until we make a change of variables. So you see, there are some processes which also seem to be reasonable to model systems with memory. So you may understand it like the media is different. So then a particle diffuses. The random scaling somehow changes. Yeah, and the fractional Brownian motion is a process like a Brownian motion but with memory, so to say. Okay, so you see, we have a kind of reasonable process, and this process has a governing equation, which also of a similar type which we have considered before. Moreover, there is a result of the year 2016. Two authors have shown that another randomly scaled Gaussian process, but it was again fractional Brownian motion with some parameter times some particular random scaling. Another randomly scaled Gaussian process solves even time and space fractional heat equation. So you see, we have the same equation, which is this time and space fractional heat equation. And we have two types of processes which have this equation as a governing equation. One type of process is this, which was written here, this psi alpha time changed by inverse subordinator. And another process was some process like this. So randomly scaled fractional Brownian motion. Two completely different types of processes can be used to solve the same equation. So that's why we have questions. So we would like to consider this type of equations. So these are evolution equations. If this memory kernel is just one, we are coming back to evolution equations which we have considered on Monday, Tuesday, and Wednesday. If memory kernel is not just constant one, then it is a generalization of the evolution equation we have seen before. So we consider such equations where L here is the generator of a Markov process, or more generally, it is a generator of a strongly continuous semigroup on some Banach space. K is some memory kernel. So the question is, So which classes of stochastic processes can be used to solve such evolution equations? Next question. So we know that these two guys can be used to solve time and space fractional heat equation. So what is common between them? So why these two classes of processes solve the same equation? And probably there are some other processes which solve the same equation. And another question is that we are particularly interested in processes of this type. So the question is how many equations can we solve using these processes? So these are the questions which have motivated our research. And now it is supposed to present you at least a little bit of results of our recent research. So there are two papers of the last year devoted to this topic. So we will start and we will see how much we can survive. Okay? Okay, so generalized time fractional evolution equations. So we consider equations which we have already seen. So L is the generator of a strongly continuous semi-group on some Banach space, and K is a memory kernel. We consider the memory kernels, we consider a very general class of memory kernels. So we do not assume that they should be of convolution type, so nothing like this. So, but we assume that the function K is good enough in the following sense, that the assumption 1 is satisfied. So assumption 1 is that my K is a measurable function, such that this suprema is finite. So what does it mean? It means that with respect to the second variable, my kernel is a little bit better than L1 function. So we have this 1 plus epsilon. But when t tends to 0, this norm may explode. We have dependence on t here and here. So this norm may explode, so we have a trouble when t tends to 0. But this trouble should be controllable in a proper way by some power function. Okay, that's all. This is a very mild or even weak assumption. So the question, which processes xt solve this equation under assumption 1? Theorem, first theorem. So having the memory kernel K satisfying the assumption 1, we construct the following function. It's a function of two variables, t and lambda, which is just a power series with respect to lambda, with coefficients which depend on t. And these coefficients are defined in the following way. So the zero coefficient is just 1, and all subsequent coefficients are calculated iteratively from the previous coefficient via the memory kernel K. So this means that all the coefficients, they pop up only from K. Hence, roughly speaking, the whole function phi, big phi, is constructed from K. And this assumption on K is enough to show that this function is well defined. And as a function of second variable, it is well defined on the whole complex plane, and it is even the entire function. Okay, so having the memory kernel K, we construct the function phi. Now, if we want to have some stochastics, we need another assumption. Assumption 2 is that the function phi for each fixed t, and if I here consider minus argument, so that is in this series, I need to consider this minus now. So the assumption is that this function of a minus second argument can serve as a Laplace transform for some random variable. That is, there is a random variable t behind this function, such that this function is just a Laplace transform of this random variable at. This CMF means completely monotone function. I assume that you don't know what does mean completely monotone function, but it is there is a definition of this class of functions, and there is the theorem that a function may serve as a Laplace transform of a probability measure concentrated in the segment from 0 to infinity if and only if it is a completely monotone function. So there is a class of functions which are Laplace transforms of non-negative random variables. Okay, so the assumption is that my function phi is exactly of this type. So there is some stochastics behind it. So under these two assumptions, assumption 1 and 2, we have proved the following theorem. This is called subordination principle. So under assumptions 1 and 2, we can define the operator, which I denote as phi of t and L, and it is defined in the following way. So if you were yesterday and followed my lecture about the subordination, then you see that this is the subordination of the semigroup generated by L. Here, Tt is the semigroup. Yeah, so you see, this is the equation. This L is the generator of the semigroup Tt. So I use the semigroup Tt and subordinate it by means of the what is AT? Each AT is a random variable which is non-negative. Yeah. So we can do it. So this integral makes sense. It's a story how to prove it, but this integral makes sense in this context. So under assumptions 1 and 2, this integral makes sense. And moreover, this integral solves this equation. So ut given by this integral, that is given by the subordination, solves this equation. So this is the main result. And now let us have some examples to understand what. But the statement is that for this class of equations, yeah, so we know that L generates a strongly continuous semigroup. So K corresponds to the function phi, which corresponds to the family of non-negative random variables. So the solution is given again in terms of subordination. We take semigroup which corresponds to L and subordinate it by family of random variables or stochastic process, which corresponds to K. But caution, this as a process is not a Markov process. Okay, so example. Oh, first remark. If the semigroup Tt with generator L also has stochastic representation, for example, if the generator L corresponds to Markov process, then the semigroup Tt has this representation, as we have discussed the whole week. Then I can insert this plug-in into this formula. Again, as yesterday, this integral means that we just integrate, we take expectation of this guy, inserting instead of a random variable a of t. So this integral is just this type of expectation. If now instead of t, I insert this representation, taking into account that I have two independent processes, I consider two independent processes, then the solution is given in this way. The solution of the advanced evolution equation star is given by this Feynman-Katz formula. So if a of t is just t, we are back to the classical setting. And now a of t is a random variable, a family of random variables, which correspond to this memory kernel. Okay? And psi is again a Markov process which corresponds to L. So this all is a generalization of what we have seen the whole week. So just a small pause for you to accept this. So once again, this is the main result, that we are able to solve such class of equations under very mild assumptions on the kernel, memory kernel K. And in comparison, so if K is just identity, this memory kernel is just an identity, 1, so constant function 1, then we are back to classical setting, and the corresponding A of t is just t. So this corresponding random variable is just t. And we are back to the classical setting. The solution is given in terms of a Markov process, which corresponds to A. But now, if K as here, so there is some random variable A of t behind, and then the solution of this equation, again, is given by subordination. Not again, but is given by subordination of the solution of classical evolution equation and this random variable of t, which corresponds to the memory kernel. Of course, so if we have any representations for this semi-group, we can use them. So all what is known in classical setting, including Chernoff approximations, Feynman-Katz formula, everything, can now be lifted to this new class of equations with this extra memory kernel. And the lifting is just by inserting this subordination. So if we have a classical, a Feynman-Katz formula, which we have seen yesterday, for a classical equation, then this equation with memory kernel has a solution which is Feynman-Katz formula, where instead of t, I insert the corresponding random variable at. Okay? Okay. Well, since we have started to discuss these processes, they should appear as well. So we consider a special case of theorem 2. Namely, we have assumptions 1 and 2, and we assume one more thing. We assume that our memory kernel K is also homogeneous. Namely, that we have this homogeneity condition for some power theta, which is strictly positive. So it turns out that in this, if my kernel K is homogeneous, then the corresponding function phi is also, in a sense, homogeneous. And I can reduce everything to the function phi at point 1. And actually, this means that the corresponding family of random variables also is a kind of homogeneous in the sense that sorry, in the sense that I can split the dependence on time and dependence on omega, so randomness, into two parts. One can show that under this assumption of the memory kernel, one can take this family of random variables in this way. A is a random variable which corresponds to the time point t equal to 1 times t to the power theta. So we have split randomness and dependence on time. So what does it mean? Let us look at the example. So this is a memory kernel which pops up in the time and space fractional heat equation. So this is the basic memory kernel ever considered in the literature. So you see this memory kernel is of course homogeneous with theta equal to beta. Starting from this kernel, one can calculate the corresponding function phi. And it turns out that this function phi is given in terms of the Mittag-Lefler function. And for such Mittag-Leffler function, it is known that the function is completely a monotone function. That is, it satisfies the assumption number 2. So taking, for example, SL Brownian motion, so 1/2 Laplacian, that is, here we have a Markov process, which is a Brownian motion. And using theorem 2, we obtain that the solution of this time fractional heat equation is given by the stochastic process xt, which is just Brownian motion subordinated by this random variable a of t. And since we have a homogeneous kernel, as a of t, we may take this product, random variable a times t to the power beta. Moreover, we know that Brownian motion is a self-similar process, or stable process, with a stability symbol 2. That's why we can pull out this a from here to here. Now it is a random scaling. It is not a random time change anymore. It is a deterministic time change, but we have a random scaling inside instead of that. So this is already a randomly scaled Gaussian process. Moreover, this random variable for each fixed t, this random variable has the same distribution as this random variable, where this is slowed down Brownian motion, and this is the fractional Brownian motion with first index beta half. So all the random variables which are written here, they have the same distribution. So not as processes, but as random variables, so one-dimensional distribution. So all these guys may serve as stochastic solution for time fractional heat equation. And what is written here, it is exactly gray Brownian motion. So generalized gray Brownian motion with alpha equal to beta. Yep.
So here for the time fractional heat equation, it means here is there a fractional Brown motion?
Well, we have discussed time fractional heat equation starting from 9 o'clock, and we have discussed different processes which may solve this equation. In particular, one of them is like this one. Another one will appear in a few minutes.
So here for t base, it means the time change, but not for the fractional motion.
I'm not sure that I have understood you, but this is the time change Brownian motion. But this is any stochastic process which has a given one-dimensional distribution.
For this time change Brown motion,
Yes.
it's still Gaussian. No. So it's no.
It's not Gaussian, and this is also not Gaussian because of this random scaling. So without it would be Gaussian, but because of this, everything is not Gaussian anymore.
So it corresponding the time fractional heat equation.
Yes.
Thank you. I'm still another question. It also a Markov process?
No, this is the point. As soon as we have a memory kernel, TTS, K is a memory kernel. So as soon as we have it, no Markov processes anymore.
So if it's not a Markov process, it still can corresponding PD.
There is a corresponding PD, but not for the transition probability, but for probability density function. Yeah? And so you know, in the classical setting, if we have a Markov process, it is enough to know its probability density function to reconstruct all finite dimensional distributions. Yeah. So from one-dimensional distributions, one can reconstruct more finite dimensional, having this transition kernel. And transition kernel, somehow, if we start at 0, yeah, it corresponds to a probability density function. But here, the governing equation is the equation for probability density function. That is, it defines only one-dimensional marginal distributions of the process. And that's all. All higher dimensional marginal distributions are not defined. I mean, they can be different. And you see here, so we have completely different processes with the same one-dimensional marginal distributions.
So usually for the non-Markov process, it doesn't produce a semi-group.
Yes, that's why here we don't have a semi-group. So this guy here is not a semi-group because here we don't have a family of convolution of measures. Convolution semi-group of measures. We don't have it. For each fixed T, we have some probability measure concentrated here, and that's all. So semi-group is inside as an ingredient, but after doing this operation, we are doing something which is not a semi-group anymore.
So can we say something about this why it continues with T?
We can state the following. Yeah, so this is the solution of this equation, that is the initial condition is satisfied.
So UT here, UT is continuous with T.
UT is just an element of my Banach space X from the domain of the generator.
So that means if even it's not a Markov, it's not a Markov process, we can still have the Feynman-Kite formula.
So you see, so this is what I wanted to stress here. So we have evolution equations which we have considered the first 3 days. They are written in this way: utx is equal u0 of x plus integral from 0 to t, it's integral version, lu as x ds. So yesterday, so all 3 days we considered the differential version of this equation. But this is the integral version, yeah? So differential version looked as this. And we have initial conditions. Yeah? So as soon as L generates a strongly continuous semi-group, which corresponds to Markov process, we can solve this Cauchy problem by a Feynman-Kite formula. Yeah? We know everything, roughly speaking. Now we have added a memory kernel. So, and it breaks everything. We have no Markov property, we have nothing, but it turns out that the solution of this more advanced equation can be obtained by subordination with the solution of the classical without K. So this semi-group, this corresponds to the case where we don't have K. So we have this gives rise to my semi-group, and hence this gives rise to Feynman-Kite formula. I don't talk about it. And then we consider a bigger class of equations with memory kernel, and the solution is always is like a subordination of the solution of the classical corresponding equation without memory kernel, plus the extra procedure. We subordinate with respect to this family of random variables which correspond to the memory kernel.
Thank you.
Yeah, so the whole apparatus for classical case, for this case, can be lifted to this new case, to the case of fractional rule, so to say. Just adding this. So all that we know about the semi-group, like Feynman-Kite, Chernoff approximations, perturbations, whatever, all representations or approximations for the semi-group here can be lifted to this formula and we obtain the corresponding result for this higher class second etage, second level equation.
So what we will call this solution name? Mild or weak?
So we didn't call it somehow because it's just a publication of last year. Just a solution. Okay. I still need a few minutes to, because you see, we have obtained this guy. It is what is written here in this particular example. But let us obtain this guy. So it is a theorem number 4, or corollary, not a theorem, just a corollary. So consider the special case. So we have not yet assumed that, but now assume that my kernel K is of convolution type, that is, it depends on the difference between T and S, and that the Laplace transform of this guy is given by 1 over h for some Bernstein function h. As soon as we have a Bernstein function, we have the corresponding Levy process with non-decreasing paths, so subordinator, whose Laplace transform is just given in terms of this Bernstein function. As soon as we have a Levy subordinator corresponding to Bernstein function h, we may consider the generalized inverse process, and it is then the inverse subordination. One can also show that in this case, so for any Bernstein function h, this inverse subordinator is again a subordinator in the sense that it has non-decreasing paths. So the statement is that in this case, one can check that this inverse subordinator has exactly the needed Laplace transform. That is, I guess somewhere should be written. Yeah, so that this inverse subordinator corresponds, has Laplace transform given in terms of the needed function phi. That is, in this particular case, as this A of t, we can take the inverse subordinator. In this case, we obtain exactly this type of processes. So Markov process which corresponds to the semi-group L, time changed by inverse subordinator. Okay, example. So the same example. My memory kernel as it is always in time fractional heat equation. And you see this is, it is of convolution type. So it corresponds to the, so its Laplace transform. Now we have calculated Laplace transform of such things today already many times. We noticed that the Laplace transform of this nice function t to the power beta minus 1, here gamma of beta, the Laplace transform of this guy is exactly u to the power beta. And this is a Bernstein function, okay, not u, lambda, it doesn't matter. Yeah? The power function of power beta. So this is the Bernstein function. Sorry, it's minus beta. So it has the form 1 over, this is 1 over u to the power beta. So this is 1 over a Bernstein function. Yeah, that's why we are just in the setting of this corollary, and hence we can take inverse beta stable subordinator as my A of t. So for this particular equation, time fractional heat equation, that is with beta here and with gamma equal to 1, so not fractional Laplacian but just Laplacian. For this just time fractional heat equation, we obtain a lot of processes which serve as stochastic solution of this equation. So these are the type of processes which pops up as limits for continuous time random walks, so this left type of processes, they are limits of continuous time random walks, scaling limits. And this type of processes, they are generalized Gregorian motion and other randomly scaled Gaussian processes. But also there are some guys in the middle. And other processes which also serve as stochastic solutions. Yeah, and one more remark. Yeah, in this case, which is discussed by Carola before, this equation can be rewritten, so to say, in differential sense, like here. And then this differential sense means that if we have a kernel of this type, then on the left-hand side should be a Caputo-type fractional derivative, which corresponds now to the Bernstein function h, and is defined in this way. So if my if my Bernstein function is just a power function, then we obtain just the definition of Caputo derivative, which we have seen today. But it can be done for any Bernstein function. So for a big class of functions. And hence, this type of equation includes in particular equations with Caputo derivative of order beta, a mixture of Caputo derivative of different orders, or distributed order Caputo type derivatives, so this is just the statement that there are many equations in the literature. So fractional analysis is a very wide area today. There are a lot of publications, and there are a lot of definitions of different fractional derivatives, and people consider a lot of equations and try to solve them. So the statement is that many equations which pop up in the literature and are solved, so to say, one by one for each particular equation, they are all actually special cases of our equations considered here. Okay, I am almost finished, don't worry. So it's just to persuade you that this is a strong result, everything is a strong result. And so recall, we have an explicit way how we deal. So we consider evolution equation with this kernel k here. Starting from k, we construct a function phi, and then we recover random variables which have a Laplace transform given by the function phi. So starting from the equation, we have the explicit way to get to this A of t, this family of random variables, which serve as a solution, which serve here in the solution. Okay. In particular, this helped us also to obtain. So this is a nice example, but we have also obtained some further examples, which were not known in the literature before. In particular, we considered a big class of memory kernels K, which correspond to some big family of operators which appear in fractional calculus. I will not discuss any details, just to give an impression for you. So we consider terrible family of kernels given by a big family of special functions. It is the third generalization F3 of the Gauss hypergeometric function. So it's a big family, 5-parameter family of special functions. With their help, we construct a big family of memory kernels. For this big family, don't try to remember, it's just to get the impression. So for this big family of memory kernels, we are able to calculate the corresponding function phi. It looks as follows. It is a 3-parameter Mittag-Leib function. So it's a special function which is studied, well studied already. This is a gamma function, and this is a 3-parameter Mittag-Leib function. So this is its representation. It is known under which conditions this all gives rise to completely monotone functions. That is, there is a random variable behind, and hence Yeah. And hence we are able to solve evolution equations with such terrible memory kernels. Yeah, again by subordination. And for subordination, we have to use random variables with such Fourier transform, Laplace transform. In some special case, just in this very special case, we obtain the kernel which pops up in the governing equation of generalized Gray-Brownian motion. That's all. I'm finished. Thank you for your patience. Have any questions? If no, then no.
Thank you once more for this course of your lectures. So you saw here modern results, and you can understand what modern representation do now. So you can see it here. You will have slides, yes, so you can read it, and if you're interested, you can contact us and you can work maybe together. Yes, who knows. And now we will have a break until 2 p.m. So please, we have lunch break, and see you in 2.
Do you have the email of Yana?
So it's a Gaussian